Okay. Now, at the end of class last time, we were we learned how to translate English expressions to formal methods, and we started this. There's this handout that I'm going to give you in a few minutes, and everything that's on the screen is in the handout, so you don't need to take notes on this. I just want you to think about it. And remember, we said one of the English phrases that translates into a Boolean expression is if-then. So if you have an English sentence that says if P, then Q, the way you translate that into the Boolean expression is P implies Q. Right? We learned that yesterday.
You left us with a cliffhanger.
I did. Now, yeah, I did leave you with a cliffhanger. Now, but we started with this one. We said P, comma, if Q. Now, do you remember? This wasn't the cliffhanger. Yeah, this is Q implies P. Just because you have the if switched in order, it's if Q, then P. So you remember that one, yeah?
Yeah.
And now this is the one that we were puzzling about at the end of class last time. It's P only if Q. So what we've done is here we said P if Q. Now the only difference between number 1 and number 2 here is this word only.
That's a big
Only if only the woodpecker cried welcome to tree.
I mean, the truth table has one more way it can be false.
Oh, do you think it's not an implies? I mean, because a truth table for implies has only one entry where it's false.
Right, but this one would have.
But you're saying that the truth table for this would have 2 entries where it's false?
It would.
Oh, that's not correct. I give you a choice. Here's it.
Is it not?
Oh, do you think it has a not in it?
I think maybe.
Maybe. That isn't correct either. That isn't correct either. Okay, here I'll give you a multiple choice then. It's one of these two. It's either P implies Q or it's Q implies P.
It's Q implies P.
No. Q plus Q.
So if it's Q implies P, you're saying that this is basically the same as that, and the word only doesn't change the meaning of it.
P implies Q.
Dang it.
All right, let me give you okay. Actually, you're right. It is.
This is spitballing.
It is P implies Q. But let me see if I can give you an example to convince you. You guys know, how old must one be to be the President of the United States? 85?
35.
Oh, 35. Yeah, 35. Everybody should have. You guys, every U.S. citizen should have a copy of the Constitution of the United States. I have one right here, actually.
You give us out one every year.
Okay, you should read it and know what's in there, because that's the supreme law of the land. Anyway, in one of the sections here, it says that in order to be the president, you have to be 35 years old, right? So think of it this way. You are the president only if you are 35 years old. Now, does that mean if you are the president, then you are 35 years old, or does it mean if you are 35 years old, then you are the president? Well, definitely not the latter, because otherwise everybody who's 35 would be the president, right? So actually it's this. It's the same as P implies Q. And the example here, be careful, this is not the same thing as expression 1. Okay? So does everybody understand now then that if you put the word only in here, it actually switches the order of the implication? And so the truth table does in fact still just have one entry where it's false. Now, does everybody get this? Does everybody see how that works? Okay? All right, so here's the next one. P if and only if Q. Well, what's happening here? If you say if, this is the same thing as what? P if Q and what? P only if Q, right. So it's both. So it's both P implies Q and it's what? And Q implies P. So this is going both ways. All right? So it's the same as Q implies P and P implies Q. And it turns out if you do the truth table on this, if you do the truth table on, if you do a column for Q implies P and another column for P implies Q, and then you do the AND of those two columns, you will get the truth table for P equals Q. You can try it if you want.
They both have to be true to be true, right?
No. They both have to be true for it to be true, or they could both be false for it to be true. They have to be the same. Okay? Does everybody get that? And by the way, sometimes, have you ever seen this if with two F's?
Yeah.
If and
No.
if.
That if with two F's is an abbreviation for if and only if. So frequently in math, that's a very common word in math. It's a math term.
If.
Yeah, if. If, and it means if and only if, and it means P implies Q and Q implies P. In other words, it means equivalence. All right?
So it's the same thing.
Yeah, equivalence is the same thing as P implies Q. Yeah. Equivalence is the same thing as if and only if. Right. Is everybody clear on this? Yeah? Are we good? Okay. So, this next one is called sufficient. Have you ever heard the word sufficient?
Never.
I've heard the word.
Oh, come on. Never in your whole life. You've never heard. I don't believe
I've
that.
heard of the word insufficient.
Insufficient. Yeah.
They're always like, Mason is insufficient.
it's always, yeah.
It's about me.
I am insufficient for up to the task. Anyway, so what does it mean to be sufficient? And I'll give you another hint here. This says P is a sufficient condition for Q. It's going to be it's either going to be P implies Q or Q implies P. It's going to be one of
Isn't
those.
that P implies Q?
Oh, let's think about it.
Same as if P
No, it's Q implies P.
Oh, we have a difference of opinion.
began.
P does not follow from Q.
I think it's a disjunction.
I think it's
Oh, like or? Disjunction is or? Or are you just throwing that out to confuse us? Okay, let's think about it. Suppose you are in a class and you go to the professor in the class and you say, what is it going to take for me to pass this class? And the professor says, well, you know what? I mean, you have all of these quizzes and you have to do your homework and stuff like that. But I'll tell you what. To pass this class, it's sufficient that you pass the final exam. Now, what is the professor saying? It's sufficient that you pass the final exam.
If you pass the exam, then you'll pass the class.
Yes. It means if you pass the exam, then you will pass it, regardless of anything else. So which one is it? So is it P implies Q?
Q implies P.
So it's P implies Q.
Oh, sweet, right.
Same as if P, then Q. In other words, passing the final exam is a sufficient condition for passing the class. So if you pass the final exam, then you pass the
So
class.
it's the same as if.
Well, but it's if
P then Q.
it's if P then Q. It's not the other way around. But now, so let me ask you this: have you ever heard the word necessary?
Q implies P.
That's the same as only if.
Yeah, it's necessary. So you come to the after the class is all over, you come to the teacher, and you said, I did all of my homework. You said I did all of my homeworks. I passed the I did all the quizzes. I did all this work, and I didn't pass the final. And your professor says, well, in order to pass it's necessary for you to pass the final in order to pass the class. It's necessary, right? I mean, it doesn't matter. You can do all that other stuff, but if you don't pass the final, you don't pass the class. So the teacher is saying something fundamentally different from what for number 4, right? Is everybody good?
Not her.
No problem. Okay, now, so are you with me here? Okay, so what is it? Is this P implies Q or is it Q implies P?
Q implies P.
Q implies P.
Yes, Q.
Because what you're saying here is that if you pass the class, then you had to pass the final because it's necessary to pass the final. Now, is everybody clear on this? This is really common logic terminology. Yeah? Okay, so the next one's easy now. P is a necessary and sufficient.
P equals Q.
Yeah, because now it's P is necessary, which is Q implies P. P is sufficient, and P implies Q. So if it's both of them, it's the same as what? If and only if necessary. Okay, equals. The same as P equals Q.
That's cool.
Now, does everybody see how this necessary and sufficient? And necessary and sufficient, that crops up a lot in logical arguments in English. In fact, I had a renter, actually, a student rented a room for me once, and she was a Seaver College graduate. She went on to law school, and when she was studying for her LSAT to get into law school, all of this necessary, sufficient logic stuff, they have to do all of this. Legal people have to understand all this logic stuff, and this necessary and sufficient is real common English terminology in logic arguments, because they have to be able to follow the logical arguments of a case, and like that. Okay, now what do you think about the word whenever?
Whatever.
Not whatever. Whatever. It's whenever.
Q implies
Q implies P.
P follows Q.
Whenever sounds suspiciously like the word what?
If.
If. Yeah?
Yeah, so if
So this would be the same thing as P if Q. So would that be Q implies P or P implies?
Q implies P.
Good. It's
Say that one.
Q implies P. So whenever means the same thing as if. All right? And here's another one. Provided that. What do you suppose provided that means?
Q implies
P
Only.
P implies Q.
Well,
Provided that, so it's a pre, so it's Q.
Q implies
P
P.
happens if Q.
Provided that.
so is this Q implies P or P implies
I
Q?
think it's Q.
P implies
Q
Q.
implies P.
It is Q implies. It is Q because provided that means the same thing as if.
Wait, really?
Are you with me?
Oh, right.
Whenever means if. Provided that means if. Right? I mean, it's just another English word for if.
Provided only provided.
Well, now, if you say only provided, then we're back to the only switching it. Is everybody good on this? How about unless? Now, this is a little tricky.
Flip it.
Or it does
Oh
not
no,
follow.
negate it. Like
Sup-
the
If
slash
Q, then
dot
not P.
thing.
Well, no, this doesn't have a not.
Q.
Q does not.
Oh, sorry, it does have a not. This one does have a not in it.
Not P.
Suppose we say I will buy it unless you do. See, there's only one item in the store, right?
Unless.
And you're in there together. And suppose you say I will buy it unless you do. What does that mean? If what?
If they buy it, I won't.
No. I will buy it unless you do. What does that mean? If you what?
If you buy it.
Buy it. They won't.
No. I will buy it unless you do.
Unless.
If you bought it, that means they didn't.
No, they get it first.
So Q.
So not Q implies P.
Yeah, very good. It's not Q implies. It's if you don't buy it, I will. Right?
Yeah.
Are you with me?
Yeah.
So yeah. So same as not Q implies P. If not Q. See, I will buy it unless you do means if you do not buy it, then I will.
Oh, right.
Are you with me on this? This is really a little more complicated now than, yeah? Are we good? Okay, and here's another one. Now this one is, now this is P unless not Q.
And then just make it Q implies P.
And that,
P implies Q.
yeah, which is it? Q implies P or P
I
implies
think
Q?
it's Q.
Oh, we have a difference of opinion.
It's the first one,
Unless
just they
it's still a
cancel each other out.
precondition.
Right. So wouldn't it just be Q implies P then? 'Cause it's
Yeah.
Not Q.
Okay,
Yeah, no, you're right.
Okay, good.
oh, now we finally all agree that it is Q implies P. How about, so here's the example. I will take another course unless I do not pass this one. That means what?
No idea.
Come on. You're in this course, right? You want to take the next course. You say, I will take the next course unless I do not pass this one. What does that mean? If I if pass this one,
then I'll-
then I'll take another course.
That's like
Okay.
double negative.
It is kind of, okay?
Exactly double negative.
But they cancel.
Yeah, we will actually see about how that double negative thing cancels later. Okay, and now here is an interesting word. It's actually not a word, it's a punctuation mark. It's the semicolon,
Oh no.
right?
It's just like-
So what does it mean?
And-
P semicolon Q. That means P and Q, right? And here's another one. It's the comma. I think we've done this one before. Do you remember where we did the comma before and it means and? Oh, you remember? Remember where that was? It was on, remember we had didn't we have an inference rule?
Possibly.
Oh, yeah.
It was like
Yeah.
x
Yeah.
equals y, comma, y, transitivity. Yes, it was transitivity. It was x equals y, comma, and then the conclusion was x equals z, right? And this we said means and, is an example of it. Comma means and. Semicolon is like the comma, it means and. All right? And then but, how about P but Q? It also means and. Right? I can do that, but so can you. That means I can do it and you can do it. Okay, so here's the handout.
Better than you. That's what
Shall
I was thinking.
Okay, so all of this stuff is on this handout.
That wasn't a word.
Okay.
I just said. I was just like, oh,
sweet.
oh, sweet.
Okay, now there's one more thing that I would like that we need to do before we go on to chapter 3. Today, I think we're going to actually do our very first proof today. This is exciting. This is what we're all leading up to.
Really?
Yeah, if we can get through this next thing in time, and I think we can. I want to say a word about equality versus equivalence. Now, some of this material is not in the book, so you might want to, this stuff you might should jot down. All right, equality.
Is that equals versus equivalence?
Yes. He said, is that equals versus equivalence? And that is what it is. Equality is equals, equivalence is equivalence. All right. First of all, we're going to do a compare and contrast. Don't you hate it when those teachers say compare and contrast? Okay, so the compare, here's how they are the same. Equals, well, here. Equals and equivalence have the same equals and equivalence have the same truth table. All right. Now okay.
Yeah.
Now actually there's one more thing that we need to remember, and that is, do you remember one of these is for Booleans and numbers and the other one is just for Booleans? Remember which is which?
Equivalence is only for Booleans.
Equivalence is only for Booleans. Equals is for Booleans and numbers. Okay, so let's say equals is for numbers or Booleans, whereas equivalence is only for Booleans. Boolean, actually, does anybody know where the word Boolean came from?
Man.
Yeah, George Boole.
Yeah.
George Boole. He was-
George Bush.
And so it's named after him. He investigated the mathematical. Okay, but now there are, okay, so
I think we have.
He was the first person to define true and false.
well, I think truth, I think truth was a concept that predated George Boole. I mean, truth goes all the way back to the dawn of play. Yeah. Okay, so there are three differences other than these. Okay, and here's the first one. The first one is that equals has higher precedence.
But why?
then equal, because it's just defined that way. You know that precedence table that we had at the beginning? That's just the way our author, or well, the people who devised this system, that's just how they defined it. You can define it however you want, and as long as you're consistent, that's the rule. You see what I mean? And so equals, if you look on that precedence table, equals is way up here and equivalence is way down here. Okay, so equals has higher precedence than this. Okay, so tell me this. What happens, suppose you have this expression, x times y equals 0 equivalence x equals 0 or y equals 0.
Do the equals first.
Yeah, where, if you were to put the parentheses here, where would you put, I mean, what does this mean? Like you said, you do the equals first. Yeah, it's x times y equals 0, equivalence. Now, does anybody remember what the equals compared to or?
Equals is higher than that?
Equals is higher than or. So it's like x equals 0 or y equals 0. This is not 0 or y.
Right.
Yeah, and this is also not 0 equivalence x. Does everybody see that?
Got it.
So because this equals has higher precedence, we do not need parentheses here, right?
But we'd like it.
No, we want to RUP. We have removed unnecessary parentheses. So this parentheses here would be unnecessary, right? But that's how you do interpret it.
Couldn't we just get rid of precedence and just put a whole bunch of parentheses everywhere?
Well, yeah, you could, but wouldn't that be ugly having all those parentheses all over the place? Okay, so no need for parentheses.
Plus, you have to have some precedence. Parentheses won't solve all problems in every case.
Whatever, you can do squiggly lines.
Okay.
Those like square.
Now comes the one that, this one's going to crop up. Well, this one does crop up all the time. But this one also crops up all the time. And this is, I'm going to ask you this over and over again, you know, in the future. So another one of those. Okay. So equals is conjunctional. Equals is conjunctional, while equivalence is not.
What do you mean by that?
What do we mean by conjunctional? What the heck does that mean? All right, now I'm going to give you an example from algebra. You are actually familiar with this, I think, with the conjunctional meaning of equals. Okay? And I'm going to give you, I'm going to do one with, we're going to mix equals with less than. Suppose we say B equals C is less than D. Now have you ever, does this make sense to you mathematically? Have you ever seen something like this before in math?
Yes.
Yeah? Well, what does this really mean? What does it mean? What does it mean B equals C less than D? How can B equals C be less than D? What does that mean? How could B equals C be less than D? If B equals C is a Boolean, how can a Boolean be less than a number? What does this mean? You understand what I'm saying?
Yeah.
What does this really mean? This is really just a shorthand. You know,
Wait, because the less than is low precedence, yeah. Which I
well, in math, I don't know.
Wouldn't it just be like B or C is less than D?
Well,
B and C is less than D.
but what do you mean B and C? Because how can you if B is a number, how can you say number? These are numbers. I
was
like,
gonna say
They're the
Boo's,
same
But you can
number.
use
B is a Boolean and C and
transitivity.
D numbers.
huh?
How about B is a Boolean and C and D?
No. These are all integers. Suppose these are all numbers. In algebra, this is a very common kind of an expression in algebra, but what does it mean?
Means that B and C is
They're both less than D.
This means, here we go. This means B equals C what?
In parentheses.
And
And
And what?
is less than D.
C is less than D.
So that's what we meant by B and C are less than D because they're the same.
Well, no. This is, well,
I said
oh, yeah, okay, but you're using transitivity. Well, you were mixing concepts. Now, okay, look, what do you remember what we call this symbol?
Conjunction.
And it's conjunction. Now, do you see why this is called the conjunctional meaning?
yeah.
It's because because this is really just an abbreviation for this conjunction. Are you with me?
Yeah.
Does that make sense? This is the conjunctional meaning. And similarly, what about this? B equals C equals D. What does that mean?
They're all the same.
No, well, you can conclude that, but really,
B equals C and C equals
yes.
D.
Yeah, it means B equals C and C equals D.
And then B
Right.
equals D.
Well, that comes from the that's a conclusion that you make due to the transitivity. And what are the 4 properties of equality? What are the 4 properties of equality?
I forget.
Yeah, you forget. Oh my gosh. I have failed.
Functionality.
What is it? What is it? What is it? What are the letters? RSTLR,
Reflection.
reflexive, S, symmetry, transitivity, Leibniz. Good. Do you know what each one of those are? Okay, so does everybody see what conjunctional means?
Right, so that doesn't make sense in the Booleans, right? If those, for the bottom one, if those were equivals.
Well, yeah, now let's do equivals, because equivals has another, in contrast to being conjunctive, equivals has a different property. Okay? No. Good guess. Good guess, but it's not disjunctive. It's associative. So here, 3. Equivals is associative. Equivals is associative, while equals is not. Right? Now, what do we mean by associative? Here, I'm going to give you an example.
I'll let you take this one.
Like associates.
That's good. Example. Suppose we have this state. What's the definition of state?
Variables with numbers.
List of variables and their values. So suppose we have this state. B false, C false, and D true. That's a list of variables and their values, right? Now consider this. Now watch this. Parentheses, B equivals C, parentheses, equivals D. Just let's consider what this is. So, what is this? What does this whole thing equal?
Yeah.
Well, I'm going to do it the other way just to show you that it's associative. So what if we so if we put the values in here, this is going to be false equivals false equivals true, right? And then the false equivals false is what?
True.
True. So this is true equivals true, and then true equivals true is what? True. Does everybody see that? Does everybody understand that, how we evaluated this Boolean, right? Okay. So now let's do it, but now let's put the parentheses around the C equals D. So now let's do B equivals C equivals D. And now we're going to do this one first, right? So now this is going to be what? False equivals false equivals true this time. But now this is going to be false equivals what? False equivals true is what? False. But now false equivals false is what? True. And what do we notice about this? These are what? These are the same. These are the same. Right? Those are the same. So what this says is that it doesn't matter where you put the parentheses with equivals. Equivals is associative. Okay? But does this work? Does this work for equals? I mean, in fact, here, let's demonstrate that. Okay, so here's our point. Since equals is conjunctional, it cannot be associative. Okay, so here's our, so, you know, let's do it like, let's do the same state. Let's say we have B equals C equals D, right? Now, what did we say this means?
C equals D.
This would be B equals C and C equals D. So this is B equals C and C equals D, right? And so what would this be, with our thing over, what would this be?
That'd be false.
False equals false, and
False equals true.
false equals true. And then false equals false is what?
Null returns false.
Wait. False equals false? Same truth table as equivalence, right? True. So, are you with me on this?
Yeah, I said the whole statement.
Oh, you are jumping ahead. And
False.
false. So then true and false is false, right? But you know, if we did it like this, you know, if we did it B equals C equals D, I mean, if we did it associative, you know, we're going to get like what we did over there. So this would be false equals false, right? Equals, what was D? True, right? Is everybody following this? And then this would be what? True equals true, but true equals true is true. So I mean, it can't be both. See, it's either conjunctional or it's, are you with me? It can't be both. So the conjunctional meaning, so these are not the same.
There's actually a need for both of them.
Well,
Both equals and equal values.
yes, there is a difference, and this is the difference. Okay, so our point here is that these are not the same, and the conjunctional meaning is not the same as the associative meaning. The conjunctive meaning is not the same as the associative meaning. Now,
Doesn't that seem a little abstract though? Why couldn't you just put the parentheses on the equals and make it?
yeah, you know what? You can do that. In other words, you can, this is a legal expression with equals,
Right.
but the thing of it is that it does not mean the same thing as this.
Right.
Where
Are you with me?
Okay, good.
Yeah, are you with me? So that was a good point. This is a legal expression with equals,
Doesn't change when you do that.
but equal, yeah. Now, I'm here to tell you guys that if you ever dare mention this to your math people, they will not know what you're talking about. They will freak out.
That'd be funny.
because this characteristic between equals and equivals, this is something that's unique to this formal method system that we are learning, and mathematicians do not go here. They don't go here and they don't use this.
That's a universal truth, right?
Well, everything that we're doing is true, but we're just setting up, but what we're doing is we are setting up our logic system according to some rules that are a little bit different from the way the mathematicians
So
use
the
them.
mathematicians, they would have a different result.
Well, the mathematicians don't mix. Here's the thing. They avoid the equivals is what they
They don't
do.
use it at all.
They hardly, they don't like it.
Right, but if they were to use it, then this would.
Well, yeah, but they don't go there. You know, they don't do formal methods. They do, mathematicians don't do formal methods. Mathematicians do informal methods. That's what they do. But in computing, computers are, I'm telling you, computers are based on logic. When you go down, we actually have a course, it's called computer organization, and we wire together these little chips on these breadboards, and we hook these wires up, and inside that chip, there is actually an OR, and inside that chip, there's an equivals. In that chip. So computers are built I mean, computers at their lowest fundamental level are based on equivalence and or and not. Okay? So that's why, and this is the the mathematical logic for computing.
That's why it's in the major.
That's why it's what?
That's why it's in the major.
Yeah.
I'm sorry, we have to take the,
You don't have to.
Oh, you don't have to. I mean, you don't have to take all the courses. That's just one of the ones.
One of the
But
two
it's
left.
yeah.
but you have to pick one.
Okay.
What is the other one? Operating system.
Which one's more fun?
I'm thinking both, so.
See, that's what I'm
Well, yeah. Okay. But are we?
The same last four letters in our first name.
Okay.
What? His name's Jason. What? Jason.
Good point.
He lied.
Makes sense.
His name's Ben. He's a superhero. He didn't turn into monsters.
All right. Now, okay. Here we go. Okay. Now we're going to go. I was hoping we would be able to get to chapter 3, and since you guys are such a great group, and we were able to speed right along here, and you know the difference between P if Q and P only if Q. We got that all. we got all that down.
No help from the viewers at home.
Now starts something big.
Now we're actually starting.
Now this is where we're actually going to things.
Welcome to class.
Welcome to full minutes.
Yes.
They watch it. They're like,
Proposition 8.
Propositional
8.
calculus.
Calculus.
Propositional calculus. Now, this first, the first part of formal methods that we're going to deal with is called propositional calculus. Now, little vocab here. There's two words here, propositional and calculus. So first of all, well, what does this mean? First of all, what's
Signed in between.
Propositional and calculus.
okay? First of all, what is calculus?
Study of change.
Rocks, small.
I like that
stones.
one. Study of change. It's good.
Oh, well, actually, no. That
the
study of change, that is the definition. Whenever you use the word calculus, the first thing that pops into your mind is the traditional calculus of functions and changes and derivatives and integrals, areas under the curve. But that is just the calculus, that's the calculus of change. But there are other, this is a different kind of calculus. In general, the word calculus means it's reasoning, processing or reasoning by symbols, by manipulating symbols. Okay, so
It also means small rocks. It does. Look up calculus in the dictionary.
process of
Here, I'll show you with my iPhone.
reasoning
I don't have to go to Urban Dictionary.
by.
Go to normal dictionary.
Okay, so it's a process of reasoning by manipulating symbols. So, in the calculus that you guys are familiar with, the symbols are like, the integral symbol or the dy, dx. That's the change you were talking about. Those are the same. But our symbols aren't going to be the integral symbols or the dy. Our symbols are what? Conjunction, disjunction, implies. Okay. Are you with me? So those are the symbols that we're dealing with. So that's guy. And now what is a proposition?
See? Latin, calculus, a small stone used for counting.
Oh.
Yeah, that's the etymology of calculus, a small stone, but it's used for counting, yeah.
Yeah, I learned that in Calc 1. That's all my teacher talked about the whole time. He was like, you gotta use those small stones.
Wow.
Gross.
What a loser.
And then he also talked about the calculus in your teeth the whole time. What?
Okay.
Yeah, there's
Okay,
calculus in your teeth.
we're getting a little off topic here. So, what is a proposition? A proposition is a declarative sentence that is either true or false. A declarative sentence. That is either true or false. Okay? And let me give you an example, because not all sentences are declarative. Suppose Okay, here's a declarative sentence. I hate to use the same example I did before.
Aren't questions not declared?
Correct, they are not. So for example, here's a declarative sentence. This table is red.
It has to end with a period.
Nonsense.
Well, that
I mean,
is a statement that is either true or false. It happens to be false, but it is a proposition. It is a proposition. This board is white. That is a proposition because it's either true or false. But how about this? May I please have a cookie?
That's not a proposition.
That's not a proposition, it's a request. See? So not all sentences are propositions. Are you with me?
I get it,
Yeah.
because you know how there's some people that like, you'll like say something and then people will be like false. You know,
What?
like they'll try to be like
Not
false root. And you'll be like, "No, it's a
Okay, so now, does everybody see the difference between a proposition, a statement that is either true or false?
What did you say, like, I propose we go to the cafeteria?
I propose that we go to the cafeteria. Ooh, that is an interesting
Not sure
statement.
if I'll-
It's not true or false.
I
but
propose that
you're
we go.
Proposing.
Yes, it is.
I think that falls under a request.
It is a
It is, so I don't think that's a proposition.
Okay.
That is not, but it does have the word propose in there. Boy, you guys are sharp. You're gonna keep me on my toes here. Okay, now, two more words that we need for vocab. First one is an axiom.
Universal truth.
All right.
chaotic.
First of all, an axiom is a Boolean expression.
Means it's crazy.
It's the name of my youth ministry.
Wait. It's a Boolean expression. What's a Boolean expression? What's an expression?
True or false?
True or
No,
false?
either.
No.
Has two answers. True or false.
No. An expression. What's the definition of an expression?
Let's not do that.
Has
Why? Because you don't know it yet?
constant or variable.
Constant or variable. If E is an expression, okay.
The only
So an axiom is a Boolean
binary prefix, infix, operator.
Here we go.
Boolean expression that defines the properties of Boolean operators.
That was the secret. It would be called axiom.
Okay? Now here is the key fact about axioms. There's this, and this is crucial. Axioms are never proved.
What?
Axioms are never proved. Okay? They are assumed to be valid. They are assumed.
Why don't we just prove them?
You can't. What we are going to do is we are constructing a logical deductive system. And in any logical deductive system,
Wait, are this
there are certain axioms that you have to start with. Look, and this is true even of not just of formal methods, this is true of any logical argument. Every logical argument, if you have an argument with a friend over and you're arguing over some issue,
Like you assume that that's called a disk.
you have to have some common basis for your argument. Are you with me? That you both agree with, that you then can try to logically deduce, either one thing or something else.
Euclidean postulates.
Yeah, and how many axioms? Did you know that? Euclid's axioms. Do you know how many Euclid's axioms there were?
No.
80.
No,
4 or 5.
no, 13. You don't know that there's 13? And did you know that if you go to Santa Monica today, there's 10th Street, 11th Street, 12th Street,
14.
and then what's after 12th? Euclid Avenue,
Euclid.
and then 14th, and then 15th. Yeah, you didn't know that? Next time you're in Santa Monica, check it out.
Who's Euclid?
Euclid, he was the famous geometry. You haven't heard of Euclidean geometry?
Euclid's synonymous with Euclid. It's always 13 is a bad luck number.
But anyway, those are like those 13, Euclid came up with 13 axioms, and from that he was able to prove all this whole big geometry, properties of circles and rectangles and
Right.
being able to bisect an angle and all that kind of
Okay.
stuff. Yeah. So anyway, every logical system has to start with some axioms that are assumed to be valid that you don't, and then what you do is from those axioms, what do you prove? What's the next word?
What's the meaning of life?
Theorems. Okay? So, here's the definition of a theorem. A theorem is either one, an axiom, or two, a theorem that is proved equal to an axiom or a previously proved theorem. To an axiom or a previously proved theorem. Okay? So what we're saying is, now which is it? Is it all axioms are theorems, or is it all theorems are axioms?
All axioms are theorems.
Yeah, all axioms are theorems, but not all theorems are axioms.
But wait, why not?
Some theorems are.
Because some theorems are proved from previously proved theorems or axioms.
But those theorems are proved by axioms.
No. Here, actually, let me give you. We won't be able to do a proof today, but let me give you a picture of.
This is what axioms look like.
Come on. Okay.
We have 2 minutes left,
Yeah. Here, let me just show you.
yeah. Sorry.
Okay. So here's our famous table of precedence, right? Okay. And here's some basic types that we will look at. And here now is the first set. This is the first set of axioms and theorems that we're going to start with on Thursday. Now look at this. Here is 3.1. It says axiom, associativity of equivalence. So this is an axiom. And what does this say? This says that if you do P equals Q first, and then you equivalent that with R, are you with me? That's the same thing as doing what? Q equals R first, and then doing P equals
How
that.
do you prove that?
No. Yeah, we did, but we did it with truth tables.
Which doesn't.
No. Okay. Now, let me tell you about the truth table. The story of a truth table. Truth tables are very, very limited. And what we're going to do is, even though we can, we have this truth table idea, that has severe limitations. And so what we're going to do is we're going to use proofs by deduction as opposed to proofs by truth tables. Okay, so this is a different approach. Are you with me? And so the truth tables are going to go by the wayside. Okay. Now here's another axiom: symmetry. What does this say? P equals Q.
Equals Q.
Equals Q equals P. So that's symmetry, right? And then this next one is axiom, identity of equivalence, and it's true equals Q, right? Okay. Now take a look. Each one of these has the word axiom. I will never ask you to prove any of these 3. I cannot ask you to prove because they are axioms. They are not proven. On the other hand, we are going to prove the reflexivity of equivalence. In other words, we're going to prove that P equals P.
Using the axiom of identity.
Using what went before.
Axiom of identity.
But, no. All I'm trying to say is the difference between an axiom and a theorem.
Yeah.
You see what I'm saying?
I still don't get how we didn't prove the first one.
Because we are no longer going to have our proofs be based on truth tables.
Truth tables are gone.
Truth tables are, we are going to abandon
When you
proofs.
say prove something, you mean using a proof. Like,
Yeah.
not explaining why it is this.
I will show you, yeah, starting Thursday.
Prove doesn't really mean
Do we really
explain
have
why
to
it
prove
is so.
that a table equals a table?
No, we're going to be done with truth tables.
Okay.
Okay, so, all right?
But did you hear what I said? Like, so when you say prove, you don't necessarily, you mean using a proof rather than just explain why it is this.
Yes, using a formal proof. We actually did
That's what you're throwing me off.
we
Technically, prove
yeah,
by English language.
right.
3.1.
Okay, all right, so Thursday is going to be a big topic. All right, see you then.